So let's look at finding the solution to polynomial equations. Okay, I'm going to start with an example. Let's solve the quadratic z squared plus 4z plus 6 is 0. One way we can do it, complete the square. I don't see if we can see any others. Is there any z2 and 3? No, it's not adding up. So completing the square is the way to go with this one. So z squared plus 4z, and if you're wondering what on earth does b on 2a mean, by that I mean the a is the number in front, the coefficient of z squared, and b is the coefficient of z, right? A. Okay, so this is just a shorthand. In order to complete the square, we have z squared plus 4z plus b over 2 lots of a, all squared, plus the 6 minus what we've added on in order to keep it the same. Okay, just a trick here to use a method to open up options. What we add, we also take away to keep it all equal to 0 at the end. We have z squared plus 4z plus 4 over a is 1, so 4 over 2 all squared plus 6 minus 4 on 2 all squared. This then gives us z plus b on 2a all squared plus the 6 minus 2 squared, 4. Okay, this b is 4, 2a is 2, so 4 over 2 is 2, so we have z plus 2 all squared. 6 minus 4 is 2, so z plus 2 all squared plus 2 is equal to 0. So there we go, we factorized it. And one more trick, we're going to use our trick where we use I squared is equal to minus 1, again to open up options for us. And we end up with z plus 2 all squared minus 2i. So where we had plus 2 before, we've got I squared here, which is minus 1, so we have to put a minus here to keep it the same. So we have z plus 2 all squared minus 2i squared equals 0, which we can then factor into difference of perfect squares. Z plus 2 minus square root 2i in parentheses times z plus 2 plus square root 2i in parentheses is equal to 0. Okay, and there you go. All right, we've been able to find that we now solve that using the null factor law. First factor will give us z equals minus 2 plus square root 2i, and this one here will give us z equals minus 2 minus square root 2i, okay, or z equals minus 2 plus or minus root 2i. All right, first one. Let's have a look now at the polynomial here. Let's have a look at this cubic polynomial here. Now, where do we begin with this? All right, well, one thing we could do is we could just try guess a solution. We expect that there will be, these have got real coefficients. Okay, so we expect that there's going to be 2 complex solutions. Okay, that accounts for 2 of the 3 solutions because there must be 3 because it's a cubic. So we guess the third one is going to be a real number. So 2 complex and 1 real. Okay, well, that being the case, why don't we just have a guess? Z equals 0 is clearly not going to work because we'll be left with 3 on the end, and that's not equal to 0. We try z equals plus 1, well, that's really going to be even worse. 1 plus 3 is 4, plus 5 is 9, plus 3 is going to give us 12. So that's not going to work either. Maybe we go the negative way. Let's try negative 1. So p of negative 1 is minus 1 plus 3 minus 5 plus 3. Well, that all adds up to 0. So that works. So that means z equals minus 1 is a solution. Okay, so that's a solution. Well, if that's a solution, then taking minus 1 on the other side, z plus 1 is a factor. Okay, z equals minus 1 is a solution, z plus 1 is then a factor. So let's divide, polynomial division, z1 into our cubic here. Okay, and let's see what we end up with. Okay, so, all right, z into z cubed is z squared, then z squared times all that gives us z cubed plus z squared. We're going to subtract that from the original here, so z cubed minus z cubed is 0. 3z squared minus z squared is 2z squared. 5z minus 0 is 5z, 3 minus 0 is 3. Okay, now z into 2z squared gives us 2z. All right. So 2z times all that is 2z squared plus 2z. Subtracting that, we get 0 here. 5z minus 2z is 3z. 3 minus 0 is 3. Okay, now z into 3z gives us plus 3, and then plus 3 times all that gives us 3z plus 3. Subtracting those, we get 0, so 0 remainder. So that divides exactly in. Okay, great. All right, so that leaves us now. The original polynomial, p of z, can be written as z plus 1, our factor, times the dividend here, z squared plus 2z plus 3. And we're going to set that to 0 because we can now, much easier to solve that now. Okay, here we go. All right. So we've got z plus 1 times z squared plus 2z plus 3, z plus 1. Now here, let's do a little bit of the completing of the square here. So z squared plus 2z add on 1, okay, plus 3 minus 1, what we've added, we're going to take away to keep it the same. When we do that, we have z plus 1. Then this can be factorized. This is the usual familiar one, z plus 1 all squared. You're used to doing that with quadratics. Okay, factorize it on the cross, however you want to do it. Z plus 1 squared. Here, 3 minus 1 is 2. Okay, so next line down, z plus 1. Then we have z plus 1 all squared. And what we can do here is, again, that old trick of I squared is minus 1, opens up options for us. It helps us find the complex factors, of which we know there's going to be 2 because of the complex conjugate factor theorem. And so we're adding I squared. We've also got to change the plus to a minus to keep it the same, and that then gives us 2 options. So next line down, we have z plus 1 times z plus 1 minus root 2i times z plus 1 plus root 2i. There's our 2 complex factors. Here we are, that's all equal to 0. So null factor law says z plus 1 is 0, which is z equals minus 1. We knew that from before. And solving for the 2 complex factors, setting all this to 0, we get z equals minus 1 plus root 2i. This one here, we get z equals minus 1 minus root 2i. And we there have our 2, altogether our 3 solutions for the original polynomial. And it really was just a matter of just having a quick guess and check to see which one works. It's usually often the quickest way to sort of go around things. Okay, that's it.